In this situation, ladders are used to form right triangles. Suppose we know the height of the wall and the width of the moat. How long should the ladder be to reach the top of the wall?
Hello, my name is Tom Apostle, and I'm Director of Project Mathematics. We produce computer-animated videotapes to show young people that mathematics is understandable, exciting, and eminently worthwhile. What you're about to see are excerpts from a workshop that brought together a number of teachers who have had success using our videotapes in the classroom. They represent a variety of grade levels from various parts of the country, and they are here to share their experiences with one another. We'll begin with a discussion of the videotape on the Theorem of Pythagoras.
The kids today, they've got MTV, they've got their slick magazines, they've got everything that catches their attention. And sometimes I don't think our math books, although they're intended to, they don't catch the kids' attention and get them excited. And that's the thing that really made me happy about this video, is my kids saw it and they were sitting up and they were paying attention. And when things happened, when things jingled or jangled or did whatever that it did to catch their attention, I saw my kids getting excited about the Theorem of Pythagoras.
First time that they watched this, they were very excited about the animation and the computer graphics, and they were like, "Oh, run this back again! I want to see this just one more time." And we also used it as an introduction. Then I also used it as a summation, and they were, after we had explored the topic and really gotten into it, then it was more of an aha situation.
Karen, you said kids say, aha, let's stop and let's see this again. We don't always have the time to do that if we show the video from beginning to end. So what we tend to do is we don't show the prerequisites. If I need to stop and explain something, I can do that in the classroom with a visual aid on the blackboard, and it just allows us a little bit more time to discuss some of the proofs and how we could use this video further. And the kids just love all of these videos. They're a terrific motivational tool. I find that when I bring in the VCR into the classroom, the kids, oh, a math video.
The thing I found was that when I brought it in the classroom the first time was the kids were used to boring math videos. They weren't real anxious to even see it because they thought it was going to be sleep time. As a couple of years have gone along, I found kids asking me when we're going to see this video, and kids from other classrooms asking me if they might come in and see it. In geometry, for example, when we came to proofs of similar triangles and we looked at that a figure that was drawn on the legs, the area of those two figures would be equal to the area that was found on the hypotenuse, that they just immediately said, oh, that's the teapot problem. They pointed out that just, you know, they were thinking back to that.
And we do a lot of work with Pythagorean theorem in 3-space, and I would hand them a model, usually something such as this, and we would talk about all the relationships between the slant height, when you can substitute in and continue on, and there are about 4 or 5 relationships that you can work with on that.
We teach a course for liberal arts majors at Cal State Northridge, which is required. So it is appropriate to say that the majority of students who enroll in this course are there under protest. They're not happy about taking this course. And I found that the videotapes, especially the Pythagorean Theorem videotape, is something that allows me to set a tone for the entire course. Showing the videotape allows a wide range of options to explode for them. The real-life situations, the idea of dissection proofs. I show the entire videotape. They feel very comfortable. They are motivated. They want to know more. And then I use the videotape as a springboard. It can take me into Fibonacci sequences. It can take me into non-Euclidean geometry. And the luxury of using that tape is that I can tap into what turns the students on the most.
One of the things that I pose is that can you find something about Pythagoras that I don't know? And of course, that becomes a real game, and I've learned some interesting things. This year I had, one of my students did a baseball card on Pythagoras and drew a sketch on the front of what he thought he looked like, and then on the back it told all the statistics and all the things about it.
The discussion that went on when they got in their small groups, I was just going, wow, this is great. These kids are really thinking about these things. The things just start falling into place after you've used it a while. It doesn't happen the very first time you show it, but you just have, it's not like you can sit back and let the kids glean all this information from it, because every time I see it, I see, oh, yes, there's something new that I didn't notice before. So.
And then after we completed basic introduction and did the text work, did the computer activities, then I went back and showed the video again, as you said, in a summation. And it was then that I noticed the kids would catch more. They'd say, oh, I didn't see that the first time. And then that was when we did take the time, if they wanted to see something again, that was when they asked, well, play that back, I want to see that part again.
A lot of teachers have been turned off to the use of video in teaching for two reasons. One, because there's a feeling that it puts students in a relatively passive situation. And secondly, because we've seen so many poor quality videos in recent years, essentially talking heads. What strikes me, I think that's the term that's used. What strikes me about the Theorem of Pythagoras telelesson is that it's done two things exceptionally well. One is there's been a successful effort to identify things that can be communicated very well by means of video, and that cannot be done as well by a teacher at a chalkboard. And secondly, aside from the choice of particular content, I think the implementation is exceptional in terms of the animation, the quality of the writing, and generally the production values come across very forcefully.
It completely bypasses the verbal element, and that I think is one of the most valuable things in the video, these concrete proofs. After all, a proof is something that's convincing. It doesn't have to be in the standard mathematical format. And these dissection proofs and the balancing of equations, showing an actual balance, that's something that strikes very deep and seems to me important at every level, from kindergarten to graduate school.
And when you've got this kind of video and workbook together for really free, because it's available to school districts, then you can do the kinds of outstanding things that you see other teachers modeling at your conventions with much more elaborate equipment, like a software package or something like that.
More than 50% of my students are ESL, English as a Second Language. They don't speak English very well. And they don't, then I had some deaf and hard of hearing students as well, so they can't hear at all. And yet they understood the video. It was perfect for, they could really get the video. They understood what was going on. I didn't need to translate. I didn't need, it was self-explanatory because of the great graphics. It's really wonderful. It really helped them. I saw them using all kinds of little pieces of paper. We cut them out, we rotate them around a pencil or whatever so they could visualize what it looks like what the solid looks like. It was very useful for that. So I used it for all my classes.
I just gave them this packet and said, do something with this and write up what you did, what you learned, or what someone should do about it. And their responses to that were very, very positive. Again, they weren't insulted by the idea that I was using manipulatives at the college level. In fact, I have one student, I asked them to write at the end of this experience what they thought the purpose of the experience was. I didn't want to tell them what it was. And one student wrote, to actually manipulate the theorem and bring it into the student's full understanding and realization that, yes, even I can make this work. If the Babylonians can do it, so can I. So again, it's what everyone is saying here, this positive reaction, this I can do it. Oh, this is interesting. It's not boring.
We had this one kid who came in and watched tape. It was the polynomial tape, 6 or 7 times, over and over, studying every frame practically. And he came to me and he said, hey, this is ridiculous. I want to do this at home. So we made a copy, and I wasn't actually sure that it wasn't a copyright violation, but I'm kind of emboldened to admit it in light of your...
Well, on the tape, it's supposed to say, at least, you know, go ahead and copy it on the tape. It says that, so.
It's not a copyright.
This videotape can be reproduced for educational purposes under the conditions described on the label.
The tapes are getting out, but the workbooks don't always get there with them. And the workbooks, to me, makes the tapes really, it doubles the depth and the usability of them. So I've used the tapes for a year before I saw the workbooks. And after I went through the workbooks, I saw many more ideas to do with it.
What we've been really saying, here we have a set of tapes that covers some excellent mathematical ideas, has universal appeal to a wide range of students, and is readily available, and the price is right. Like, you know, it's just the best deal for everybody, teachers, students, together.
Hi, we're conducting a poll for Project Mathematics. What can you tell me about the number pi?
Pi? Well, it's sort of like 22/7, but not exactly.
It's 3.14 something, I think.
Well, doesn't it have to do with the area of a circle?
It's the circumference of a circle. No, it's diameter. No, it's the circumference of a circle.
Pi is the ratio between the diameter and the radius. Wait, that can't be right.
Pi is the magic number for circles.
We start off with a visual aid, and I have cut this circle into smaller and smaller fragments, and I've had the students shade them or color them so that they could line up the darker triangles, so to speak, and then the lighter triangles on top. So the students can visually see how a circle can be made to look like a parallelogram, or as the triangles get smaller and smaller, a rectangle. And then when I show the video, I find, especially with this particular proof, the kids say, we did that. I understand it. I could see it. And what's nice about the video is it does it so much more cleaner than the students do.
Divide the disk into an even number of equal slices. Rearrange half of them like a row of teeth. Fill in the open spaces with the other half like another row of teeth. The new figure is almost a parallelogram, with the same area as the disk. If we repeat the process with smaller and smaller slices, the curved sides of the teeth eventually become more and more like a straight line, and the parallelogram becomes more and more like a rectangle, with base pi r and altitude r. So we see that the area of the disk is equal to pi r squared. the same result found by Archimedes.
I also like about the story of pi is the connection to history. And that somebody just didn't wake up one morning and say, this is the area of a circle.
Well, of course, everybody finally associates pi with a circle, but I like the emphasis on the non-circular uses of pi. I just thought that was neat. And I think it's important here to mention with all these videos how they do emphasize and more than satisfy the National Council of Teacher Mathematics standards. And of course, the best part of it all is that it leaves a very good taste in the mouth, a positive taste in the mouth of the students who are using these materials and saying, I like that, let's do some more things about that.
And the beautiful thing about a VCR is you do have a fast forward button and you do have a pause. I think it's a big mistake to show the video 3 times and go through it from beginning to end without it. You have to remember video is relatively new to people my age, and we have to see it a much longer period of time to absorb than the kids who've grown up on video games. So when I show the history of pi the first times through, I don't get into the Buffon needle problem and that kind of thing. I show the beginning with the measuring, and I fast forward to some of the history of pi, and I'm very careful about editing it, and it's set up very easy for that.
It's very interesting because you see students will come up with different things that grab them. The beauty of these tapes is that it enables me to personalize the class and respond to what they find interesting, especially in a liberal arts class. I think the students, especially even by the time they get to the college, they still see mathematics as fragmented. Okay, we have algebra, and algebra has nothing to do with geometry, has nothing to do with calculus. And I'm able to use pi as the thread so that we can see that you have pi, probability, calculus, geometry. That is a nice technique that I use. The other thing also I think about that tape, which I guess all the tapes do, is it shows the multiculturalism of mathematics. You know, you bring the Chinese in, and it's a very nice way for students to understand that human beings do mathematics all over the world.
For me, I guess the heart of mathematics is proving and persuading people of some normally complicated result. I like very much the sections on the Buffon problem and the series, but the concern I have about that is I don't think you're really showing the student why it is. I think essentially saying, hey, later on you will learn that, and I don't know if there's any way to get around that problem.
And one of the great virtues of these tapes is it makes proofs concrete. Instead of being thrown a lot of formal logic, which even professional mathematicians don't understand, it shows you why it is so. So I think that's very important. But mathematics doesn't move ahead solely by means of proofs. The more important part of mathematics is conjectures. That is, things that people feel might be true and try to explore. So presenting a certain amount of what comes in the future without a full explanation, as long as it's not overdone, and I have no objection to those of you who are at different levels edit this stuff out. But it is valuable to say, look, you're going to go ahead. You're going to learn about these things later. You may want to read about them right now, even though it isn't part of your school assignment. The idea that students should not be shown anything but what they are capable of demonstrating at that particular stage, I think that's stultifying. I think it's very good to know that there's a whole world of mathematics out there, and fortunately, developments in graphics have brought a lot of this material, like fractals, home to students who can't possibly understand the roots in complex analysis. Yet it's interesting. And so you can't prove it then. So what? Go on.
We can also scale solid objects. If one solid object is obtained from another by scaling, the two objects are similar.
This is my method of enlarging a figure. And what I have here are 2 rubber bands, same size, tied together. And all I'm doing is I'm looking at the knot. And this is just a way of enlarging. And I've tried it with, whoops. And of course mine doesn't look as good, but they can see that it's twice as big. But after they know how to graph, this is Morris 1, and they graph these points and connect the dots, and then graph these, connect them, graph these, connect them. And then we have Morris 2, which is twice as much. They have to multiply 5 by 2, the x-coordinate as well as the y-coordinate, and then they see what happens. All of this is discovery. I'm not telling them what's going to happen. And we can measure the sides, and we can actually put Morris 1 on top of Morris 2 and look at the angles. And let's see if the angles are the same. Hey, the ears are the same. Every angle here is the same. Even I was amazed. I knew it was supposed to be. But I thought it was great that you could actually see this. That's when I showed them the video, because in the video shows the enlargement of this bug. And I thought that was absolutely fabulous. Expando ray. That was just another way of enlarging something, because we'd used two things already. So then I used the expando ray, just that little blurb, that little section where everything was enlarged. And now they knew, when it said 80 times, they knew what that meant. They knew that the area was not 80 times, only the lengths were 80 times. And then we talked about what the area would be like and what the volume would be like. I use a little excerpts to reinforce it, to reinforce the idea. The reason I like it is because there's an authority out there. Thank you. and saying the same thing I'm saying. And so I say, see, it's on the video. It must be true. I had several students that were in trouble all day long, but they would come to my class because they were working in groups, they were watching videos that made sense to them and they could connect, and working with stuff, that they can move and manipulate around. So I think we as teachers have to change. I am a visual learner, and when someone speaks and doesn't draw pictures for me, then I have trouble understanding what they're saying. And so if I have trouble with that, then other students that need manipulatives are going to have trouble in my class. And other kids that need to hear me speak. So I speak and I draw, and it's taken me a lot of energy. It's taken a lot of energy out of me to learn to do that, to change myself. But this year I changed myself and I changed the way I taught, and I can't tell you what a wonderful situation I had this year. The kids were fabulous.
See, when we were talking about applications, some of the most effective applications are like the monsters. I mean, they're not really practical applications. They're silly or they're ludicrous.
They're fun.
They're fun, yes. Mathematics should be fun. And I think for most of us in this room, it must have been fun, otherwise why would we do it? And let the students have a little fun with it too.
We entertain them, we dance for them, we stand on the desk, we bring in Morris and we stretch him and we shake him and we do whatever it is that we do. The videos do that excellently. They do. They entertain my students. They catch their attention. They make them chuckle when the equation goes whatever, or when pi goes at the bottom.
Similarity also explains why insects cannot grow large enough to become monsters. If we enlarge a praying mantis to be the size of a horse, the scaling factor is about 80, increasing its volume and hence its weight by a factor 80 cubed. But the strength of the legs increases like their cross-sectional area by only 80 squared. The poor creature would collapse on those spindly legs.
And that shows how easy it is to destroy monsters with a little mathematics.
The narrator's voice is very non-threatening and reassuring, and also the fact that there's good music in the background puts the whole subject of mathematics in a pleasant setting. It's very hard to feel bad about what you're seeing and threatened by what you're seeing, because it's all in a sort of reassuring setting.
But it really leaves them feeling good about themselves. And nothing beats success like a little success. And then the next time something comes off, like you say, they'll say, gee, I can really do that. I did that the last time. And that's what we need to do. We need to leave students feeling good about themselves, because they need that confidence to go on in all subjects.
with this generation of students, my experience is that if it's on television, if it's in video, it's got to be true. And it's interesting because I watched a program on PBS last night. Charlene Hunter-Galt was interviewing a whole group of black filmmakers. And it was so fascinating because these filmmakers talked about how we are molded by what we see on television. But I think that that is very, very true. And somehow my experiments in the classroom work better when I've shown the videotape first. And then when I refer back, it gives me more credibility.
Most of what we do is throwing words and numbers at students. And I think that this series of tapes and computer graphics in general remind us of something that we should know, and that is the importance of pictures in communicating mathematical ideas. So I think from that point of view, these tapes could have a spin-off effect of impacting on our other teaching as well.
We've really talked about an awful lot of things here. We've talked about using them as an introduction. We've discussed, on various grade levels, sort of dissecting it and using only certain parts for different lessons, and then using these tapes over maybe a period of days or once a week or whatever until we have done the unit that we're on, and then pull in anything that we can come up with. Writing has been mentioned, which is very, very much a very popular idea right now in mathematics, using writing in conjunction with everything. And these videotapes are perfect for this. The workbooks are very good, particularly for teachers in expanding their knowledge. Go with it. Try it. Try it a couple times.
I like it.
Yeah, it's great.
Major funding for this program was provided by the Intel Foundation. Additional support was provided by the National Science Foundation.
For information about the series, write to Project Mathematics, 1-70 Caltech, Pasadena, California, 91125.